Bismillahirrahmanirrahim. Let us continue our discussion in the second segment, which we are going to discuss on reactor-produced radionuclides. Before we proceed further, let us look at the schematic of a nuclear reactor. There are three main components. Number one is the fuel rod, which is colored as bluish. The fuel rods contain fissionable materials such as uranium-235. The second component, the one colored brownish, are known as the moderators. It functions to slow down energetic neutrons to produce thermalized neutrons. And this material, moderators, are usually made of graphite. And the third component is the control rod. Control rod are strong neutron absorbers. It functions to shield the fuel rods from one another, and the material of choice, or one of the materials that are used for control rod, is made of cadmium. So we mentioned that fuel rods, they contain fissionable materials such as uranium, and they are surrounded by moderators, which are material that functions to slow down the rather energetic fission neutrons to produce slow neutrons or thermalized neutrons. Commonly used moderators are heavy water and also graphites. And then the last is control rods. Control rods are positioned to either expose or shield the fuel cells from one another. The control rods contain material that are strong neutron absorbers. If the control rods were removed from the system, then the fission event would stimulate more than one additional nuclear fission, which could lead to the reactor meltdown. And if you insert additional control rods, it results in excess absorption of neutrons, and it terminates the chain reaction. And this procedure is usually used to shut down the reactor. So fast neutrons, those with energy 1.5 MeV, have got to be thermalized, to be slowed down with the use of moderators. And this produces neutrons with lesser energy in the range of 0.025 electron volts, and these thermal neutron interacts with many nuclei to produce various radionuclides. Reactor-produced radionuclides can be divided into two. One is fission reaction, and the second is neutron capture or neutron activation reaction. If you look at this schematic, focus on the target nuclide, which is at the center. And in a nuclear reactor, the bombarding particle is a neutron. And so by adding one neutron to the target nuclide, the product nuclide will be one square to the right of it. Because as you add one neutron, you move to the right. So you're going to get an isotope of the target nuclide. So in this case, the target nuclide is uranium-235. So by the addition of one neutron, you're going to get uranium-236, which is fissionable. The fission process, the addition of one neutron would lead to the fission process, and uranium-235 becomes uranium-236, which undergoes fission, and it fragments into smaller nuclides, which are the intention of the process. During the process, other neutrons are being produced, which would sustain the fission process. Targets are made up of fissionable material, uranium-235. U-235 absorbs a neutron, it becomes U-236, which then fragments into many nuclides, and these nuclides are separated, purified from one another using the various chemical methods. Radionuclides produced from fission process have high specific activity. If you look at the starting material or the target material is uranium, uranium-235 becomes uranium-236, but the product nuclide that you are getting could be molybdenum-99, it could be iodine-131, xenon-123, and so forth. So this is an example of products of produced from fission process in the reactor. Uranium-235 absorbs one neutron, becomes uranium-236. The product of the fission process could be a composite of radionuclides comprising of iodine-131, molybdenum-99, and so forth. So you need to conduct chemical processes to separate and purify each of these components. The last segment is about reactor produced radionuclides through the process of neutron capture. This is also known as N-gamma reaction. The target captures a neutron and emits gamma rays to produce an isotope of the same element. However, in this process, compared to the fission process, it produces radionuclides of low specific activity. Now, if you look at this table, focus on molybdenum-98 at the lower bracket. Molybdenum-98, it is shaded, meaning to say it is a stable nuclide. So when you stick this target, which is molybdenum-98, into the nuclear reactor, it absorbs one neutron, it becomes radioactive, molybdenum-99 radionuclide. And molybdenum-99 radionuclide, from this process of N-gamma reaction, it decays by beta minus to produce technetium-99m, and technetium-99m decays into ruthenium-99, which is again a stable nuclide. And this is the basis for the next discussion, which is generator, technetium-99m generator system. So radionuclides that are produced by neutron activation process or neutron capture process can be exemplified as molybdenum-98 to produce molybdenum-99, and there are also some other radionuclides that are produced using this method. If you have the opportunity to visit Malaysia Nuclear Agency reactor, you will see that they would have several facilities, radiation facilities there. And the flux are in the range of 10 to about 12 to 10 over 14 neutron per centimeter squared per second. And there are 3 radiation facilities at the central chamber, in the dry tube, and also at the rotary rack. So when you visit, please ask them to explain further on the facilities found at the Malaysian Nuclear Agency reactor. As for the target materials, either for reactor produced radionuclides and also for those that are produced using the cyclotron, there are some parameters that you need to consider. The target materials that are employed for reactor irradiation needs to be in its pure elements. This should be obtained with the required purity. For example, when you produce iodine-131 from the target material tellurium oxide, you require a purity of more than 99% chemically pure. Pure target material are sometimes produced using electromagnetically enrichment method, and this is to minimize the formation of radionuclide impurities. In summary, radionuclides can be produced by cyclotron, it can be produced by a reactor, which is either a fission process or N-gamma process. Yeah, and it can also be produced by the third method, which is the generator, which we will discuss in the next segment. Assalamu alaikum.